In this calculator tutorial, I want to show you a couple basic ideas related to integration. First of all, over here on the left-hand side, I have two ideas written on paper related to integration. I'm picking a very simple example. I've talked about the indefinite integral, the integral of x squared being 1/3 x cubed plus c. Of course, in a standard calculus course, you learn a lot about indefinite integrals, one of them being that the indefinite integral of a function is the antiderivative of that function, which gives rise to a constant of integration, or an arbitrary constant, or in other words, we tend to refer to this as a family of antiderivatives, that the derivative of this function will produce the integrand of the original problem. In the definite integral problem, lots of applications for definite integrals. One of the most basic ones that tend to be used as introductory topics is area. So if I talk about the definite integral of x squared as x goes from 1 to 3, we take our antiderivative that we got up here and evaluate from 1 to 3, which the fundamental theorem of calculus tells us to evaluate in this manner, and we get 26/3. This can be interpreted as the area under the curve y equals x squared from 1 to 3 is 26/3. I want to focus on this idea first when talking about the calculator. So in the calculator, what I'm going to do is under the y equals screen, I'm going to graph the function y equals x squared. And I believe I'm in a standard zoom. Well, the first thing I'm going to show you is under the calc menu, second trace. Under the calc menu, number 7 is the integral of f. Now, a couple main things you have to realize here. Obviously, you learned this in your Calc 1 course, but when I evaluate an integral from a to b, I'm assuming that the function is continuous and differentiable over that interval. Otherwise, there's some major issues that we would have to talk about otherwise with improper integrals. So I'm using an example here where the function we're integrating is continuous and differentiable over the integral of the interval of integration. So anyway, that being said, once I've done second trace and chosen number 7, the integral of f, I come back to my graph and I punch in my lower limit for my example, which is 1, and hit enter. My upper limit for my example is 3, hit enter, and it calculates the area of 26/3. And there's 26/3 in decimal form, and in fact it even shades the region that we just found the area of. Now, another way to calculate this exact same value, let me hit second mode and quit to the home screen, is to do the math key, number 9 I believe it is. Number 8 is the numerical derivative. Number 9 is the function integrator. So from the home screen, I'm going to hit function integrator of the function x squared, comma, as x ranges from 1, comma, to 3. When I hit enter, there's my 26/3 that we got analytically and by the graph that we did just a second ago. Again, I want to point out to you that since I have the curve in y1 back at my home screen, I could have done math number 9 and hit the vars button for variables, arrowed over to y-vars, hit function, and the equation, in this case y1. So I always enter the equation of the curve, the variable of integration, the lower limit, the upper limit, and hit enter. One last idea I want to talk about with integration is the first idea we mentioned over here, the indefinite integral. Now obviously you learned in the Calc 1 class, in order to check your integration, you take the derivative of your answer, if you will, and get back the original integrand. I'm going to show you on your calculator how you can do that. Now this is really slow, but I want to show you this anyway. Let me clear this out of here. Now, I have to be a little creative. So in y1, I'm going to do math 9 and call in the function integrator, and I actually have to use a dummy variable, if you will. So in the function integrator, instead of typing x squared like I would right here, what I'm going to do is use a different letter. I'm going to do alpha 4 and bring in the letter t up here. I can use any variable I want, but I'm using t. So I'm going to integrate t squared, comma, as t, oops, I already made a mistake. I want to say as t, comma, goes from 0 to x. Okay, and again, I'm referring to this problem up here. Forget about this discussion down here. I'm referring to this problem up here. And in essence, what I'm trying to do is have the calculator compute the indefinite integral for me. But of course, it's not going to be able to graph all values of the constant, the whole entire family. So I'm in essence, by using a 0 here, I'm choosing 0 for that constant of integration. Okay. So here's what it's going to do, is it's actually going to graph my antiderivative for me, 1/3 x cubed. It goes really, really slow, bear in mind. So generally, I don't really want to graph. What I really want to do is go to the table and make a comparison to what I know the answer is. For example, if I go back into y equals, let me type in 1/3 x cubed. And I'm going to make a comparison here. So instead of graphing, which is really slow, I'm going to do second graph and go to the table. Now before I do that, remember, in y1 I have the integral of t squared as t goes from 0 to x. That antiderivative of t squared is 1/3 t cubed. And when I go to my table, second graph, I can see that I'm getting 1/3 x squared in both of these. Okay? So I'm verifying my antiderivative. Very unique way of doing that, but it does work. Of course, the easier approach is to take the derivative of your answer and get back the original integrand. But this is a way that I can check with my calculator. And those are some basic ideas related to integration.